In this video, I will present the statement of Rolle's theorem and its proof. Rolle's theorem fits here in our big picture. It is an intermediate step that will allow us to prove the mean value theorem, and that is the reason to study it. The theorem says that if we have a function f defined on a closed and bounded interval a, b, under certain hypotheses, we can conclude that there must be at least one point in the interior with derivative 0. What are the hypotheses? First, we need the function to be continuous on the full interval, including the endpoints. Second, we need the function to be differentiable on the open interval, not including the endpoints. And finally, we ask that f of a equals f of b. As you know, differentiability implies continuity, so the first two conditions mean that f must be differentiable in the interior of the interval, but at the endpoints, it only needs to be continuous. Perhaps at this moment you think this theorem looks a bit dry and uninteresting. I think I agree, but remember, Rolle's theorem will allow us later to prove something more important, and that is why we care, not because of Rolle's theorem itself. In order to understand this theorem better, I want to look at a few examples of graphs of functions. I think the examples will clarify why all three hypotheses are there and why the theorem makes sense. After that, I will still write an actual proof, but the discussion with examples will probably be more enlightening. Okay, how can I conclude that a function must have a point with derivative 0? The third condition is perhaps the simplest to understand. It says that the value of the function at the two endpoints is the same. If I try to draw the graph of a nice function with this condition, perhaps it goes up first and then down and has a local maximum with derivative 0, or perhaps a local minimum, or perhaps both. By contrast, if the value of the function at the endpoints is not the same, then it could be increasing everywhere, and then it may not have any point with derivative 0, like this example. So this condition makes sense. It is there to try to force the existence of a local extremum. But it is not enough by itself. The function could have a local extremum at a corner, and the derivative could not exist at that point. In this example, this function is not differentiable on the interior of the interval. It fails the second hypothesis. Finally, even if the function is differentiable in the interior and it takes the same value at the endpoints, we could have this silly example. This function has a jump at an endpoint, it is not continuous, and it does not have any point with derivative 0. So there we have it, this is the theorem. All three hypotheses are necessary. Hopefully, it is now clear how the three of them come together. You may wonder, why not require differentiability on the full closed interval, including the endpoints, and be done with it? That's a good question. That would also make the theorem true. However, in general, it is good to write our theorems with hypotheses as weak as possible, because then we can use the theorem in more cases, and the theorem is more useful. That is why I will leave the theorem with just these three hypotheses. Okay, after all that discussion, I still need to write a proper proof. It will be relatively short. Here it is. First, f is continuous on AB, including the endpoints. This means I can use the extreme value theorem, and f must have a maximum and a minimum. Now, I will consider two cases. Either at least one of them, the maximum or the minimum, occurs at an interior point, or both of them occur at endpoints. In the first case, if an extremum happens at an interior point, it is also a local extremum. By the local extreme value theorem, the derivative either is 0 or does not exist, but since the function is differentiable on the interior, the derivative is 0. And in this case we are done, we found what we wanted. Now for the second case. If the function has both the maximum and the minimum at endpoints, since the value at the two endpoints is the same, then the function must be constant. But then the derivative is 0 everywhere, so there is at least one point with derivative 0. There are many. And we are done in this case too. That completes the proof. I will finish with some remarks. First, notice the parts I just boxed in red. I have used all three hypotheses in the proof. This is good because I knew the theorem would not be true without them. Second, notice the parts I just boxed in blue. I have used the extreme value theorem and the local extreme value theorem in the proof. disagrees with the big plan we had. We are finally ready to move to the mean value theorem, but before we do so, Rolle's theorem also has some other smaller applications of its own. I will present one of them in the next video.